The amazing heat pipe for class ME412, brought to you by the P-Diddy Stompers. The heat pipe was created in the early 1950s and now has applications for cooling in electronic components and space apparatus. The theory behind the heat pipe can be demonstrated in the diagram on the left. The evaporator section, located at the bottom, is submerged into a hot fluid. From there, the fluid on the inside of the heat pipe is heated to a boiling point. The steam then rises through the adiabatic section into the condenser region, where the fluid is then cooled and gravity takes it back to the evaporator section. As long as heat is being input to the evaporator, this will be a constant process. A thermal resistance diagram is shown on the right to demonstrate how heat is transferred to and from the heat pipe. We chose to model the heat pipe using a MATLAB script. This was based on equations provided by Professor Bernard.
In order to accurately test the heat pipes that were designed, a testing procedure as shown below was developed.
Here's design 1, which is a water-operated heat pipe utilizing 1/2-inch and 3/4-inch diameter copper tubing, as well as 2 ball valves. The total cost of fabrication was $20.25, and we averaged a 24 degrees Celsius temperature change. Here's design 2. It is also a water-operated heat pipe utilizing only 1/2-inch copper tubing, as well as 2 ball valves. Total cost of fabrication here was $19.25 and averaged a temperature change of 22 degrees Celsius. Here's design 3, which is quite different from the first two, is an acetone heat pipe. Total cost was $13.40 and it averaged a 22 degrees Celsius temperature change.
As can be seen, design 1 was the iteration that was most successful in extracting heat from the hot water bath. In order to more fully analyze these findings, we did a full analysis of the heat transfer for this iteration. It was found that the full temperature difference could be up to 27.2 degrees Celsius. This finding was then compared to a control test where the hot water bath was allowed to cool unaided. The temperature difference of the cooling water for this test was 26 degrees Celsius. These results were then compared for the total temperature reduction per time. It can be seen that between minutes 1 and 10, the heat pipe extracted heat faster than the control where the water bath was allowed to cool unaided.
Heat pipe design 1 was successful in extracting heat faster than water cooling unaided. The modeled and empirical data were compared, and there was a 15.7% error. Recommendations for future improvements would include modeling the heat pipe so that the condenser is out of the steam path, and to utilize fins to increase the heat transfer rate.